Alrighty, hello adventurers, and welcome to the last video for floor 9. Our insert, find, in order, and the rule of 3 are all done. 6 of our 7 self-test phases are green. Today is one method, which is remove from, and it is the single trickiest thing in the class has written all semester, really. We're going to do a few cases in Notepad first before we touch the editor. Then we're going to watch it, and we'll watch that last phase turn green. And then we'll finish this module by racing the binary search tree against floor 1's linear scan. Okay, so let's just kind of get a recount of where we're at here. Let's build our executable here real quick. We'll kind of show where we're at. So if I go ahead and if I run the self-test on BSD, we'll notice we're all good except for our remove case right here. So 6 green, 1 red. Forget says it can't find the goblin in order to remove it. Okay. Even though, so like if I run, so we notice we have an issue here with remove. So if I run forget, which is going to remove. So if I say forget goblin, it'll say goblin is not in the tree to forget. Even though we know goblin is in the catalog. Okay. The issue is that, of course, remove from is stubbed. It changes nothing and reports nothing is removed. Today we're going to write it. Adding to a BST was easy. A new value always lands in an empty slot at the bottom. Removing is hard because the node you pull out might have a whole tree hanging off both sides. And something has to take its place without breaking the rule. So let's go ahead and let's move on over to Notepad here real quick. Okay, so let's take a look here and see. We have 3 cases here, easiest to hardest. Let's say you had one, which is a leaf with no children. Okay, so in that case, we would just detach it, right? There's nothing here to relink. This would be a very easy scenario if we have to remove something, right? Just a leaf, there's nothing there, just detach. 2, a case where we have one child. So the node has a single subtree. Okay. That subtree's root simply moves up into the gap. Okay, so that's what we do in that case. The child here takes the parent's place. Okay, not too difficult. Still pretty easy. Case 3 would be there's 2 children. Okay, so here's the whole lesson here. We obviously can't just delete the node, right? Both its subtrees would float free. And we can't just pick any value to replace it, right? We know that too. There is exactly one value on the right that keeps the rule. And that would be the smallest value in the right subtree. That is going to be our, we call our in order successor. Okay. That's because it's larger than everything on the left. Okay. Because it's on the right, of course. And it's smaller than everything else on the right because it's the smallest there. Following with me okay here? So what does that mean? Well, the so here is we copy the successor's value up into this node, then go delete the successor from the right subtree. Okay. Now, there's a gift here. Okay, what is it? Well, the successor is the leftmost node of the right. Okay, subtree, correct? Therefore, it has no left child. Okay? So if that's true, deleting it is just a case 1 or 2 that we defined earlier. So that means the hard case reduces to an easy one that we have already solved. That making okay sense there? So that's the exciting thing. Okay, so let's go back here into BST. Let's go down here to this removeFrom function, and let's fill this thing in. So what do we want to do? Well, first of all, we need to say if n is equivalent to null pointer, we'll return null pointer. Then we'll say, so that would be our case of the value not in the tree. Otherwise, we'll say if value is less than the in data, then we will say n of left is equal to removeFrom n of left value and removed. All right, so notice we're just passing in here, right? We have our node, we have a value, and then we have a bool for removed. So we'll say n of left is equal to that. Okay. And then we'll return back in. We'll step outside of the if branch then. And then we'll say if n of data is less than the value, then we'll say n right is equal to removeFrom. We'll pass in our n of right. We'll pass in our value and our removed. And then we'll return our n. Okay. So then, once we're done with that, we'll say removed is equal to true. All right, so we found it. And then I'll say, let's just kind of compress this up here. And then I'll say if n of left is equivalent to null pointer, then I'll say node will get us a pointer called r is equal to n right. Then I'll delete n and return r. I'll have another branch, n of right. If n of right is equivalent to null pointer, then I will say node L is equal to n left, delete n, return L. Okay. So then I need to say, we'll do the two children. The in order successor equals the leftmost node of the right subtree. So I'll say node star successor here is equal to n of right. Okay. And I'll say while successor left is not equal to null pointer, I'll say success is equal to success left. Okay. Perfect. Then I'll say n of data is equal to successor of data. Bool discard is going to be false. And then I'll say n of right is equal to removeFrom n right successor data discard. Okay, and then we will say return n. And this should have us everything we need here. Okay, so let's go through and let's step through this thing. First of all, we find our node, okay? The same one-way descent as search. Less than, recurse left and relink the result. Greater than, recurse right, relink. That relink, that n of left, n of left is equal to removeFrom n of left, ... is the pattern I told you to watch in the first video. This is where it earns its keep. Each call returns what should sit in that slot now, and the parent wires it in. When the data matches, we set removed is equal to true. Okay? Then we have the cases below that. So after we set removed is equal to true, if there's no left child, okay, then the right child takes the slot. And then we return it. Okay? That one line there covers a leaf too, because a leaf's right child is null, so it returns null, and then the node just vanishes. Okay? If there's no right child, the left takes the slot. Okay? So we see that. So at this point then, now we have a case where both children exist. So here we're going to walk to the leftmost node of the right subtree. That's our successor in this case. So we copy its value up into this node. Then we remove the successor from the right subtree, okay, by value. And because it has no left child, that recursive call lands in the no left child case and resolves cleanly. We already set removed, so that inner calls flag is a throwaway. Okay. And then we return in. So hopefully it feels pretty good there. And just notice here we set this equal to false, and then we kind of jump back in with our remove from. Okay. So let's go ahead and take this thing to bat and see if it works. Okay. Okay, so we jump in here. Let's now self-test our BST. Boom. Remove, all correct. All phases okay. Hot dog, okay. So all 7 now, okay. And read phase 7. It removes a leaf, then a 1-child node, then a 2-child node, and checks that the tree stays sorted after every case. Now let's check out the game. Let's see if we can, let's run our catalog. So do notice there's a goblin in here. So let's forget our goblin. Okay. McCown strikes the goblin from the tree. 14 creatures remain now. Now let's run our catalog. And you see the goblin is now gone. So we run forget goblin. It's now been removed from our BST. The catalog is still perfectly sorted afterwards. Notice B, C, F, I, L, M, N, R, S, right, W. So still sorted because our remove from preserved the invariant of the BST. 14 remain. You now have a structure you can insert into, search, list in order, copy, destroy, and remove from, all of it keeping itself sorted, all of it fast. That right there is a real container. Now, if we look here, you'll notice we have a benchmark BST, so we can erase our linear scan versus our BST lookup. So let's benchmark our BST. And so you see here, we get 1,000 iterations per call. And we can see here at different tree heights, so we can see what are different queries for each one. So you see here we have a last versus it being absent. And you can see the linear. Already you can see the difference. And you see how much the linear search grows right there. Okay. Now, this is the whole point in numbers. Our linear scan gets climbing up higher and higher. You see we get up to where, in some cases there's a 2,400. That's pretty crazy there. 2,400 microseconds where, the BST's riding there more around like half of a microsecond, okay? It barely moves. That's the difference between O of n and O of log n, and it's exactly the win that binary search gave you back at floor 1, except a sorted array is painful to insert into, and this tree stays sorted through every insert and remove for free. But read the warning here that the benchmark prints. This tree was built from shuffled data. Insert the monsters already sorted in order, and every new node hangs off the right of the last. The tree becomes a single leaning line, a stick. Height of n not log of n. Okay. And lookup drops right back into linear in that case. Okay. The rule was correct the whole time. It just stopped helping. Grix built exactly like that, a list wearing a hat. Keeping the tree short no matter what order things arrive in is the one thing this floor does not do. That is going to be topic for the next floor. So you built 5 containers on pointers now. Chain, stack, queue, tree, and a BST that searches and sorts itself. It's the first one that's fast because of its shape, and you found its flaw. The shape is only fast if it stays balanced, and nothing here forces that. Next floor, McCown's tree starts leaning, and someone bends it back to level. And that is where we're going to be in the balanced hall. Hope you all have a good one. Make sure to really take a note at this as the tree height increases here. And just really take this benchmark to heart. I think it's really important. And with that being said, I will see you in the balanced hall. Bye-bye now.